Up to this point, we've been looking at macroscopic properties and observations of reactions, kind of from the outside looking in, looking at concentration, time, rates of reactions. We're going to look at one other macroscopic property of temperature and see how temperature affects the rate of reaction here in just a moment. But our learning objective for this lesson is to be able to use something called collision theory. So that's what we'll be talking about. And collision theory is looking at things, what's occurring on the molecular level, down there with those molecules as they collide, therefore the name collision theory. And we're going to use collision theory to recognize the reason for the dependence of the rate of the reaction on concentration, which we've looked at in the past, as well as on temperature, which we're going to observe here in just a moment. I like to bake. And most cake recipes occur at 350 degrees Fahrenheit ovens. That's a good hot oven, but not extremely hot. But there are some recipes that cook at a cooler oven. And I've got this pound cake recipe that I bake the cake at 250 degrees. Now, in terms of what's the difference in time? My pound cake recipe requires over an hour to cook, whereas most cake recipes will take around 30 minutes to cook. So cake at 350 will cook faster. And this is true for almost every reaction, that the rate of the reaction is going to increase with temperature. There's a few exceptions, and we're not going to get into why the exceptions occur at this moment, but it usually deals with some kind of side thing that's going on, an alternate path that is taking place for the reaction. If you think about things on the opposite end of the spectrum, let's say you've eaten already and you've got leftovers, what do you want to do? You want to slow down a certain reaction. That would be the rotting of the food, the growing of bacteria. So you're always told not to leave that food out on the counter, to put them away rapidly into the refrigerator. So you slow down that process. You want to keep it even longer? You put it in the freezer, and you can keep it for weeks and months. If you've got a deep freeze, that means you're freezing it at a really low temperature. You can keep it for even longer. So that is a macroscopic property. We see that reaction rates decrease as temperature goes down, increases as temperature goes up. We see that reaction rates decrease as concentration goes down, increases as concentration goes up. And in this lesson, we're going to see what's happening on the molecular level that causes those things to happen. I want to write a rate law, just a generic rate law here for reaction. Rate is equal to K times concentration raised to some power. We have seen that, as concentration goes up, rate goes up, and we've talked about this rate constant being a constant, but only being a constant at a constant temperature. Now, if the rate is going to go up with temperature, where does that play out? It has to play out in the rate constant K. And we see that if we plot rate constant and temperature, as the temperature goes up, the rate constant goes up. It's not a linear relationship, but it is definitely an increase in rate constant with an increase of temperature. Oh, went the wrong direction. Bear with me. Okay, so we're going to start by thinking about what's happening on the molecular level that causes the rate to increase with concentration, and then we'll look at why it increases with temperature. The first thing that we need to know about collision theory is that for a reaction to take place, a molecule has to collide. They collide with each other. If molecules just sitting there minding its own business, it's not going to want to turn into a new product. So if you could get the number of collisions to increase, you're going to make the reaction rate increase. It's going to happen at a more rapid rate. So rate is directly proportional to the number of collisions per second. So the first thing we can think about is, why does rate go up as the concentration goes up? Okay, what happens to the number of collisions as the concentration increases? Well, let's look at this little schematic of reaction. The blue has to run into the red for a reaction to occur, let's say. And the number of these spheres you see is a representation of the concentration. Now, if blue has to collide with red, the black lines represent the number of possible collisions that can occur. And we see 4 lines here, 4 possibilities of collisions. Now, if in the same size container we increase the number of the blue spheres, then we can increase the number of possible collisions to 6. So we're going to have a greater probability of these collisions occurring in a certain amount of time if we've just increased the blue. We could increase the red, and this again would be 6. We've increased the red instead of the blue. But if we increase both of them, then this is going up to 9 here. We have 9 possible collision paths that would lead to a reaction. So as you increase the concentration, you're going to increase the number of possible collisions. So that we know rate increases with concentration, this is why. Rate is increasing with concentration because you are increasing the number of collisions. Now let's think about it in terms of something that you can imagine a little bit better maybe. If I put you in a room with 3 other people, there's 4 of you all together running around the room, and I say, okay, I want you all to run in this room, and if you run into something, you just bounce off and keep on running. And you just imagine in your mind how many times you probably would run into somebody as you're running randomly around the room. Let's keep the room size the same, but let's put 100 of you running around in the room. What is that going to do to the number of collisions? If the number of you in the size of room, that would be a representation of molarity, moles per liter, as you increase the concentration, you're certainly increasing the number of collisions. So if you have to have a collision for a reaction to occur, if you increase the concentration, you're going to increase the number of collisions, therefore you're going to increase the rate of the reaction. Okay, so that's the first thing. You have to have a collision. But not every collision results in a reaction. If it did, then all of our reactions would occur virtually instantaneously. In the blink of an eye, in the snap of your fingers, the reaction would be done because molecules move very, very rapidly, way faster than you can run around a room. And there are so many collisions in such a short amount of time that the reaction would take place virtually instantaneously. So why do some reactions take minutes and some hours and some even maybe years to take place? Well, the reason for this is something that we need to understand, and that is a collision has to occur with enough kinetic energy to break the bonds that are there. Those atoms are held together with energy. We have to break those bonds, and that requires energy to do. If they don't collide with enough kinetic energy to actually break the bonds that are there already, then they just bounce off of each other. Activation energy is the minimum energy required to initiate that chemical reaction. It is that barrier. Anything less than that, molecules bounce off. Anything there or more, the reaction can take place. These diagrams are called potential energy diagrams. Let me just explain a few things about them first. The one on the left is an exothermic reaction. The one on the right is an endothermic reaction. In your past lessons, somewhere in your past, you've talked about endothermic and exothermic, and you've talked about delta H. The difference in the energy between products and reactants would be the measure of this delta H. For exothermic reactions, it would be products energy, which is a small number, minus the reactants energy, which would be a large number, and these values are negative. But as time goes by, as the reaction progresses from left to right, you start with reactions, you're going to go to products if there is enough energy to break those existing bonds and you have met that activation energy. So I will call this the mountain those reactants have to climb, the energy that they have to have in order to get over there and down to products. Now, over on the right-hand side, this is an endothermic reaction. The delta H, again, would be from across my arrow here, and this would be a large number minus a small number, and they are always positive. But the activation energy barrier that has to be overcome always starts from, so we're progressing to the right here. The arrow goes from reactants all the way to the top of the peak there. So this reaction has got a much higher activation energy barrier. The molecules have to collide with a lot more energy to become products. Up here at the top of the mountain is something called an activated complex, and it's going to be a temporary species. It is there for such short time. It's usually not even observable, but it is the temporary species formed by the reactant molecules as a result of that collision. So you could think of it as the jumbled mess of atoms as they have collided with enough energy to break those bonds. Once that activated complex is formed, that molecule or those atoms can either recombine and go over here and reform reactants, or recombine and go over here and form products. And the truth of the matter is, both of them are going to occur, but if the reaction is going to proceed to products, we're going to form C and D. Okay, so let's go back to thinking about collision theory. Molecules have to collide for the reaction to occur. You get more molecules, you get more collisions, but they also have to collide with enough energy to get over this mountain. So it's got to get over this mountain. So if they collide and they don't have enough energy, they just are A and B still. But if they collide with enough to get over the mountain, then you form products. So based on what we know at this point, why does the reaction rate increase with temperature? Well, I've got two diagrams here, and temperature 1 is less than temperature 2. So the right-hand diagram is a higher temperature. And this is a Maxwell-Boltzmann distribution of the number of molecules that have a certain speed. And let's say we know that kinetic energy, the average kinetic energy is equal to 1/2 mass times this speed squared, average speed, okay? We have to have enough kinetic energy to get over the mountain. And let's say that every molecule that has at least this speed or higher will have enough kinetic energy to overcome the activation energy barrier. So every one of these molecules, if they were to collide, could react and form products. But we raise the temperature. When we raise the temperature, this distribution changes, and this is still the minimum speed needed to obtain this kinetic energy so that it can get over the mountain. But now all of these molecules have enough energy to get over the mountain. So as temperature increases, you might increase the number of collisions a little bit, but really what you're doing is you're giving those molecules more kinetic energy, and more of them have enough energy to get over the activation energy barrier. So this is our look at collision theory and trying to explain what's happening on the molecular level that causes the rate to increase with concentration. You increase the concentration, you have more collisions, and causes the rate to increase with temperature. If you've got a higher temperature, you have more molecules that can get over that mountain, that activation energy barrier, to get to the other side and form products.